quality, monitoring manufacturing processes, and testing finished products for nutrient content and other parameters. Environmental impact of fertilizer production. The production and use of fertilizers have significant environmental impacts. The production of nitrogen fertilizers, in particular, is energy-intensive and releases large amounts of greenhouse gases like carbon dioxide and nitrous oxide. The excessive use of fertilizers can also lead to soil and water pollution, which can have detrimental effects on the environment. Applications of inorganic chemistry in fertilizer production. Inorganic chemistry plays a crucial role in the production of fertilizers, which is vital for modern agriculture. The application of inorganic chemistry in fertilizer production can be seen in various ways, such as the development of new fertilizers, improvement of fertilizer quality, and utilization of fertilizer waste. Development of new fertilizers. Inorganic chemistry allows the development of new fertilizers with specific nutrient ratios and enhanced nutrient availability. For example, slow-release fertilizers have been developed using inorganic compounds like urea formaldehyde and sulfur-coated urea. These fertilizers release nutrients slowly over an extended period, reducing the need for frequent fertilization and minimizing nutrient loss. Inorganic chemistry also allows the development of micronutrient fertilizers, which provide essential trace elements like zinc, iron, and copper to plants. Micronutrient fertilizers are particularly useful for crops grown in soils with low trace element availability. Improvement of fertilizer quality. Inorganic chemistry plays a crucial role in maintaining and improving fertilizer quality. Quality control measures include testing raw materials for purity and quality, monitoring manufacturing processes, and testing finished products for nutrient content and other parameters. Inorganic chemistry also allows the development of specialty fertilizers for specific crops or soil types. For example, acidifying fertilizers can be used to lower soil pH for crops that prefer acidic soils, while alkaline fertilizers can be used to raise soil pH for crops that prefer alkaline soils. Utilization of fertilizer waste. Inorganic chemistry also plays a role in the utilization of fertilizer waste, which can reduce environmental impacts and improve sustainability. For example, phosphate rock, a byproduct of fertilizer production, can be used in the production of phosphoric acid, which is used to make various phosphate fertilizers. In addition, fertilizer waste can be converted into useful products using inorganic chemistry. For example, ammonium nitrate waste can be converted into calcium ammonium nitrate, a fertilizer with reduced explosive properties. This conversion process also reduces the environmental impact of ammonium nitrate waste, which can be a hazard if not disposed of properly. Challenges of inorganic chemistry in fertilizer production. While inorganic chemistry has made significant contributions to fertilizer production, there are also challenges that must be addressed. One of the major challenges is the environmental impact of fertilizer production and use. The excessive use of fertilizers can lead to soil and water pollution, which can have detrimental effects on the environment. The production of nitrogen fertilizers, in particular, is energy-intensive and releases large amounts of greenhouse gases like carbon dioxide and nitrous oxide. Another challenge is the limited availability of some inorganic compounds used in fertilizer production. For example, the availability of phosphate rock, the primary source of phosphorus used in fertilizer production, is limited and concentrated in a few countries. This limited availability can lead to price instability and supply chain disruptions. Future of inorganic chemistry in fertilizer production.